Welcome back. So today we are going to be covering lecture number 18 for Physics 1112, entitled Interference and the Wave Nature of Light. What we're going to be looking at today is how does light interact with itself. Over the last few lectures we've been looking at reflection and refraction. How does light reflect off a surface? How does it refract at an interface? What we're going to do now is look at how light actually interacts with itself. The basic idea is what happens when light combines with other light. So light plus light. Well, we would think that if you have some light and some light, you should get more light. Well, if I take two flashlights and I take one flashlight with some light and another flashlight making some light, and I put them together, we get more light. So light plus light gives us more light. That seems to be obvious. If you're in a room and you turn on a lamp, you have some light in the room. If you turn on another light, you expect the room to get brighter. You have more light. Well, what if we actually look at the very simple idea that we have of the wave nature of light? What would happen if we actually have two sources of light that have a uniform wavelength and a uniform polarization? How might those two waves combine together? Well, let's take a look. Okay, let's remember this view of an electromagnetic wave. We've got an electric field oscillating up and down, a magnetic field oscillating in and out of the board, and the direction of travel is to the right. Remember, we always have this right-hand rule orientation of the electric, the magnetic field, and the velocity. So when the electric field is up and the magnetic field is out, the velocity would be that way. So we always have this orientation. Now, let's just look at the electric field. So let's imagine we've got a perfect sine wave shape electric field that is in the plane of the board, so up and down and up and down. How might we have two of those waves add together? What if we are trying to add two sine waves? How can they add together? Well, let's take a look. So here's one sine wave. Let's imagine this is representing our electric field. So it's pointing up over here and then down here and then up and then down and up and down like that. And now let's imagine that we could add another electromagnetic wave with an electric field with the same magnitude, the same wavelength, and with the same polarity. So the electric fields are pointing in the same direction. So let's add another wave. So here we go. Here's another wave. We add them together and they're in phase. Well, what happens? Well, we'll have one vector this way and we add another vector this way. What happens? We end up with a vector with twice the amplitude as the original one. And then over here, twice the amplitude down, twice the amplitude up, twice the amplitude down. So we add light plus light and we get a lot of light. So let me just draw that. So taking one wave, adding another wave that's in phase meaning whenever this one is up, this is up. When this is down, up, up, down, down, up, up. Adding them together, what do we get? We get another wave with the same wavelength. So the wavelength is exactly the same, but the amplitude is now twice as big. So we have light plus light giving us lots of light. When we combine waves that are perfectly in phase like this, we'll refer to this as constructive interference. Constructive interference. In other words, we'll say that these two waves are interfering constructively. Now, typically in ordinary everyday language, we usually use the word interference in a kind of a negative way. You might interfere with someone trying to do something, meaning you try to stop them or you hinder them or something like that. When it comes to light, interference implies no negative sort of connotation. It just means that they are interacting with each other. We could call this a constructive interaction, but the proper term is interference. So we'll say constructive interference. When two waves are in phase with each other and they combine together to give us more light, we'll refer to that as constructive interference. Now, how else might these waves add together? Well, let's see. Okay, here we go. What if, again, we have these two waves, but now, what if one of them were to move over a half of a wavelength, so something like this, or maybe one of them flipped upside down somehow, like that, we end up with a similar sort of thing. Now, when one wave is up, the other wave is down, and when the first wave is down, the other wave is up. So now our vectors are, say, we have a vector up adding to a vector down, and if they have the same amplitude, they will be exactly in opposite directions with the same magnitude. They will exactly cancel each other out. So in this case, we'd actually have light adding to light, giving us no light. Zero electric field. Likewise, zero magnetic field. So in this case, we'd have one wave that was going up, down, adding to a wave that's going down, up. So that whenever one was up, the other was down. And when this one was down, this one would be up. If we added these electric fields, what would we get? They would always cancel out, and we would get no electric field. In this case, we would have light combining with light, giving us no light. Now that seems like a very, very strange result. You might think that that would be like you turn a light on in a room, the room gets brighter, you turn on another light, and the room gets dark. Now, that doesn't happen, we know, because light that comes from lamps isn't like this, but that's the idea. We're taking light and adding light and getting no light. When we have two waves that are exactly out of phase with each other like this, and we combine them together, this is called destructive interference. Destructive interference. In this case, light plus light gives us no light. Now, how might we arrange something like that? How could we get two sources of light that would actually combine together and canceling each other out? Can we do that sort of thing? Well, yes, we can. Okay, to do that, we're going to need two coherent light sources. Now, that means they have the same frequency and they have a constant phase difference. Now, to do that, well, you might think you could have two lasers, and those two lasers might satisfy coherence. Well, the easiest way to do that is actually to take one laser and to split that beam into two sources. So that's actually what we're going to do. Let's imagine we have a laser with a beam, and we're going to allow that beam to strike two little slits, two little openings on a slide. And I'll show you what that looks like in just a second. But we're going to allow that beam, actually in this case that beam has to be a little bit wider. It's going to hit those two slits, and then we're going to have light, coherent light, two coherent sources coming out of those two little openings. So you can imagine it's like having two windows right next to each other, allowing light to pass through. But the light that's going to be passing through those windows, those very small windows, will be a single laser beam. So the two lasers coming out will satisfy our condition of coherence. They'll have the same wavelength, and they'll have a constant phase difference between the two. Okay, great, there we go. So let's imagine we do that. What's going to happen? So here we go. We've got this laser coming along, striking our two little openings, our two little slits here. Light is then going to go in all directions when it comes through the little windows, but let's focus on two rays that come out of the window and come together, and they both strike a screen. So let's imagine there's a screen over here that the light is striking, and the two rays, one from each slit, come together over here. So they're going to combine. Now, how are they going to combine? How will they interfere with each other? Constructively, destructively, something in between. So the question is, are we going to have light here, or are we going to have no light there? What's going to happen? Well, let's figure that out. So I've made the picture a little bit bigger here. Here are the two slits. We've got a ray coming out of the slit going up to the screen way over there. Another ray coming out of the second slit down here, going up to the screen way over there. And we want to figure out, are they going to give us constructive or destructive or something in between? Well, the reason that if they're starting out in phase here, we're assuming they're in phase here because they're the same light source. The reason they might not be in phase once they get over here is because this ray actually has to travel farther than this ray. Do you see how this length down here is longer than that one? Well, how much is this one longer than that one? Well, let's draw a line across here so that this ray is the same length as this one down here, so that this angle here is the same as that one here. We'll make an isosceles triangle. This lower ray then has to travel this extra distance down here. This is what we'll call the path difference. And it's that path difference, the fact that the lower ray has to travel that much farther than the upper ray, that could put them out of phase. What we have to do is figure out, what is that path difference? How far is that? Well, let's imagine that that point, whatever that point is where we're considering, let's imagine that that is at an angle of theta from our central axis. So let's draw an axis from the point in between, halfway in between the two slits, perpendicular to our slide here, and we'll call that our central axis. Now let's imagine that this point P, where we're combining the rays, let's imagine that point P is at some angle theta up from the central axis. Now, that line here is going to be perpendicular to that line there that forms the base of our equilateral triangle. So that's going to be at a right angle. Now, if we think about that, if that's a right angle and that's a right angle there, then this angle here is going to be 90 minus, or this angle is going to be 90 minus that angle, which is going to be the same as that angle. So if this is an angle theta, this also has to be the same angle theta. Okay? Now, if that's theta, let's say that the distance between the slits, we'll call that d. D is what we'll call the slit separation. It's the distance between the slits. And to be precise, that would be from center to center, center to slit to center to slit. That's the slit separation, D. Now, let's enlarge this triangle here. This is D. That is theta. That is the path difference we're looking for, and that's a right angle. So that path difference is opposite theta, so this is d sine theta. That's the path difference. That is how much farther the lower ray has to travel than the upper ray. D sine theta. Well, how is the path difference going to determine whether the two rays are in phase or out of phase? Let's go back to our picture of the sinusoidal rays and see how that affects it. Okay, so here are our two rays again. Now, let's imagine that the two rays start out in phase and they both travel the same distance. If they start out in phase and they travel the same distance, they're both going to end up in phase. In other words, they will interfere constructively. What if one of the rays has to travel an additional distance of half a wavelength? Well, if one wave moves half a wavelength more than the other wave, they will end up being out of phase, and we will get destructive interference. What if that wave has to move a whole wavelength farther? Well, then they're back in phase, and we get constructive interference. What if a wave moves a wavelength and a half? Then, out of phase again, destructive interference. 2 wavelengths, in phase, constructive interference. 2.5 wavelengths, out of phase, destructive interference. I think you get the idea. If one wave moves an integer number of wavelengths, in other words, 0 wavelengths, or 1 complete wavelength, or 2 complete wavelengths, or 3 complete wavelengths, or 4, 5, 6, 7. The 2 waves will be back in phase again, and we will have constructive interference. If one of the waves has to move an extra half wavelength, or 1.5 wavelengths, or 2.5 wavelengths, or 3.5, 4.5, 5.5, then they will end up out of phase, and we will have destructive interference. So all we need to do is look at that path difference, what we found to be d sine theta, and determine whether it's an integer number of wavelengths, an integer plus a half number of wavelengths. That will tell us whether it's constructive or destructive interference. So if this path difference, the path difference between the top ray and the bottom ray, and now I have to say I've made an approximation here. I am assuming that the screen is very, very far away compared to the distance between the slits. In other words, we might say that this distance from the slits to the screen, L, we are assuming that L is much larger than D. That kind of allows us to assume that this is a very, very small angle over here, and that this ray is almost at a 90-degree angle. Now, obviously it's not going to be exactly a 90-degree angle, but if the screen is very, very far away, that's almost a 90-degree angle, which allowed us to use the trig function that this side was d sine theta. So it's actually an approximation, but it's usually a very good approximation as long as L is much larger than d. So what do we have? The path difference, then, this d sine theta, if that is an integer number of wavelengths. So we're going to assume that m is an integer. If the path difference is an integer number of wavelengths, 0 wavelengths, 1 wavelength, 2 wavelengths, 3 wavelengths, then the 2 waves are going to be back in phase when they make it to this point, and we will have constructive interference. In other words, light plus light will give us lots of light. If, however, d sine theta is an integer plus a half a wavelength, 1.5 wavelengths, 2.5 wavelengths, then the 2 waves will be out of phase and we will get destructive interference. In other words, light plus light will give us no light. Does this really happen? Can we actually make light and light give us no light? Well, let's try this experiment and see if we can do it. This is actually called the Young's double-slit experiment. Running out of room here, I'll erase my triangle here. Young's double-slit experiment, or just the double-slit experiment. So let's try this and see what happens. Can we actually make light and light give us lots of light and no light? Let's try it.